Until now, we've been dealing with singular capacitors. Like this is one capacitor. And these examples too, each of these examples is just one capacitor, because a single capacitor is a pair of conductors, yes? But we can actually create chains of capacitors. And we'll see that having a collection of multiple capacitors gives us a broad array of possible capacitances we can create. But before we move on, let's collect our thoughts from the previous lessons. Up to now, we know that in theory, any pair of conductors forms a capacitor. We saw different interesting symmetrical arrangements of conductors, and we'll see later that they actually end up producing neat capacitance formulas based off of their geometric arrangements. But from here on out, we're going to be primarily using parallel plate capacitors for our illustrations, really just because they're the most convenient to draw. Here on the right, I've drawn our very first circuit diagram symbol. This is the symbol for a capacitor. It's just a parallel plate capacitor with conducting wire connected to each plate, kinda like this. We need symbols because we can't draw fancy, colorful images for all the components in our circuits. We need symbols to simplify that process for us if we're trying to communicate our ideas to other physicists or engineers. That's not to take away from the other kinds of capacitors, though. All of the work we're about to do can be easily translated to these other capacitors with just a little extra thought. Now then, we were talking about chaining together capacitors. There are a couple of fundamental ways we can link capacitors together. One way we can link them together is with them sort of connected parallel to one another like this. Not surprisingly, this way of connecting capacitors is called connecting them in parallel. Now, what are the implications of connecting them this way? Look at this entire left side of the capacitors. Remember, each of the plates is a conductor, and now we've connected all of these conductors to each other via conducting wire. Maybe it could be copper wire or something like that. So in some sense, they're now just pieces of one giant conductor. This entire side on the left is just one conductor then. And we remember that an important thing we know about conductors in electrostatic equilibrium is that the electric potential is constant throughout the conductor and at the surface of the conductor. This makes sense since if the electric potential weren't constant, we would have charges moving around until the electric potential were constant. Then that means since each of these plates is connected to each other, they're all at the same electric potential as each other. A completely symmetric argument can be applied to the other side of conductors. There's only one caveat though, which is that while all of these plates might be at the same potential, and all of these plates might be at the same potential, the two sides don't necessarily have electric potentials that are equal to each other, because they're not connected to each other by a conductor. There's an insulator blocking the flow of charge between them. Of course, if everything here is neutral, then everything is at the same potential. But now, what if we connect a battery to this whole configuration? We'll discuss batteries in much more detail later, including how they're fundamentally different from capacitors, but at a high level, the battery just has a positive terminal, a conductive terminal which is lacking electrons or positively charged, and a negative terminal, a conductive terminal with an excess amount of electrons. Sometimes you'll also see the symbol drawn like this, with two pairs of terminals back to back. Now, all of a sudden on the left-hand side, we have a single conductor again, and a high charge concentration at the positive terminal of the battery. Positive charge wants to redistribute itself across all these plates on the left by traveling through this very thin conductive wire. Of course, we know the mechanism of current flow is the movement of electrons, so it might be more something like electrons moving toward the battery terminal from the left plates, leaving behind excess positive charge on the plates. But trying to animate it like that might make things a little bit too cluttered. On the screen here, the charge transfer looks really slow, but in reality this happens almost instantaneously. Charge continues to flow until all of the left plates and the positive terminal of the battery are at the same electric potential, because the entire left side is just one conductor now, and that one conductor has to be at the same potential everywhere once charge is done moving. What about on the right side? The negative terminal has an excess of electrons, so these electrons want to redistribute themselves until all of the components on the right side are at the same potential. Remember, there's insulation between left and right here, so we can't have charge bridging the gap. Charge is just stuck on each side. Also, by symmetry, for each pair of plates, the magnitude of the charge on one plate is equal to the magnitude of charge on the other plate, provided the plates are really close together. Now, in the configuration we have here, we can conclude that the potential difference between each of the capacitors is the same as the potential difference across the battery. And that's actually really good news here, because we usually know what the potential difference across a battery is. Consider you might have heard of 9-volt batteries before. That means that the potential difference between the two terminals is 9 volts on each battery. You know that information as soon as you buy the battery. So that means we know the potential difference across the battery, and by extension, we know the potential difference across each capacitor. But where are we going with all this? What we want to be able to do with complicated systems of capacitors like this is turn those systems, no matter how complex, into a single equivalent capacitor. We want this equivalent capacitor to behave exactly the same way in practice as this complicated capacitor system we started out with. If we knew each of the capacitances of all the capacitors in this complex system, then our goal is to find out what the equivalent capacitance of this system is, what the capacitance of a capacitor would be, such that it would be equivalent to this complex system of capacitors we have here. So let's get started. Our first step is to recognize that the potential difference across both systems is the same. In fact, the potential difference across everything we have here is the same. The reason this is okay to say is batteries are actually designed to maintain virtually the same potential difference between their terminals for an extended period of time. So the potential difference across our imaginary equivalent capacitor is the same as the potential difference across each of the original capacitors 1, 2, and 3. In that case, we know capacitance involves more than just potential difference, so what can we say about the other important property, the charge on each capacitor? Remember, a capacitor always has a zero net charge. When we say charge on a capacitor, that just means the magnitude of the charge on either plate. Consider this junction right here. All of the positive charge that's entering this junction from the battery has to be split up between each of the capacitors. Maybe it's not even obvious how that split occurs if we have capacitors of different capacitances. But we know that the sum of all the charge that ends up on the capacitors, it has to come from the battery, right? In the same sense, all that same amount of charge needs to end up going toward the equivalent capacitor in the imaginary simple situation. If we really expect the equivalent capacitor to behave the same way as the collection of capacitors. So the second equation we can write down is that the sum of the charge going towards charging up each of the capacitors in the parallel configuration, that sum is the same as the sum of the charge going towards charging up this equivalent capacitor. Now we've got two interesting looking equations, so where do we go from here? Well, we know for any capacitor, its capacitance is a measure of how much charge it stores on each plate per its potential difference. In that case, why don't we try multiplying by the potential difference, and we're left with the charge on any capacitor as a function of its capacitance and its potential difference. We can apply this definition to any capacitor, so why don't we just apply it to all of them? The charge on the equivalent capacitor is the equivalent capacitance times the equivalent potential difference. The charge on the first capacitor is C1 times delta V1, and so on. Since we know the potential difference across each of the capacitors is exactly the same, we can simplify things even further from here and just call the potential differences across all of them delta V. It's just whatever the potential difference across the battery is, remember? In that case, every term has delta V, so just dividing both sides by delta V gives us the equivalent capacitance as a function of the initial capacitances. Very interesting. The equivalent capacitance is just the algebraic sum of all of these capacitances that are in parallel with each other. So this means in our analyses, we could replace this system of capacitors we have here with an equivalent capacitor that has this capacitance, and it would have exactly the same behavior in practice. That's honestly pretty cool, and it's also a very useful fact in the real world too. Now I proved this to you for 3 capacitors here, but in general if we have n capacitors in parallel, then this would give you the equivalent capacitance of that parallel combination. You just extend the equation up to n terms. I encourage you to try and prove this fact for yourself if you're interested. So that's one of the fundamental ways we can connect capacitors. We call this connecting them in parallel. But what's the other way? The other way we can link them together is one after the other, like this. We say all of these capacitors are in series with one another. Now what can we say qualitatively about this configuration? Again, it might look like something special is going on here, like we're dealing with fancy knickknacks of some kind, but at the end of the day, each of these plates is just a conductor, and now some of these conductors are connected together via conducting wires to form bigger conductors. That's all. For example, it might feel weird because it bridges 2 different capacitors, but it's useful to think of this collection over here as just a single conductor insulated from the outside world on all sides. Okay, fair enough. So let's think about what if we connect a battery across this collection of capacitors. How do these capacitors behave then? Once again, we're constrained by whatever the electric potentials of the battery's plates are, because the battery acts to maintain the same potential on its plates, even once you connect it to something. These plates over here then have their hands forced. Each plate is going to end up with electric potential derived from the potentials of the battery's plates. In order for that to happen, this plate on the left becomes positively charged, and the plate on the right becomes negatively charged by some amount. So now all we have to do is determine how these components in the middle will behave. The key here is that each conductor in the middle is just a plate on one capacitor connected to a plate on a different capacitor. These conductors started out neutral, so by conservation of charge, they're going to stay neutral since charge can't exit or enter by bridging the gap between the insulators. Taking this first conductor, charge is going to become polarized across it because you have an equal amount of negative charge attracted to this positive plate on the left. Then we have negative Q on the left, provided the plates are quite large and close together and the conducting wire is very thin. So we have to have positive Q on the right by conservation of charge. The two have to cancel in order to get us back to a neutral state. And we end up with this kind of cascading polarization effect here. So this one over here on the right needs to become polarized too. In that case, we also have negative Q moving over because it's attracted to the positive Q in the middle, and that leaves positive Q on the right by conservation of charge. Since the whole conductor started out neutral, so we expect it to stay neutral if charge hasn't entered or exited the conductor. Then the stable configuration of these capacitors would have the negative charge on the rightmost plate as negative Q, which came from the battery's negative terminal. Once these polarizations happen, there's no reason for charge to move anymore. What's interesting here is in this case, the charge on each capacitor is the same. If we call each of these capacitors 1, 2, and 3, then Q1, Q2, and Q3 are all equal. Now let's jump to the equivalent capacitor for the same situation. Just a single capacitor connected between the battery's terminals. Remember, we call this C sub EQ for equivalent, and we hope we can find an expression for it in terms of only the initial capacitances we had in series. So we recall that in series, the charge on each capacitor is exactly the same, because that's what creates this cascading effect we saw based on the conservation of charge. We can't end up with some of the capacitors having different charges. If the first plate is positive Q, then the plate next to it has a negative Q attracted to it, which leaves positive Q on the next plate, and the cycle continues like that until we end up with the last plate. Again, each capacitor technically has a zero net charge, but when we say the charge on a capacitor, we're talking about just the charge on a single plate of the capacitor. Then it only makes sense that the equivalent capacitor has the same charge on each plate, since it has to behave the same way as the collection of capacitors in series. If we want to take all of these capacitors in series and reduce it down to some equivalent capacitor, it has to behave exactly the same as the collection. So the positive plate has to take the same charge as the outermost left plate in the collection, and the negative plate has to take the same charge as the outermost right plate in the collection. This means the charges on all of the capacitors in series are the same as the charge on the equivalent capacitor. Now we have to ask ourselves about the other important variable, the potential difference on each of the capacitors. For that, let's think back to the equivalent capacitor. What we expect here is again for the potential of this plate to be equal to the potential of this terminal, and the potential of this plate to be equal to this terminal's potential at electrostatic equilibrium. Once charge has stopped flowing, these potential values are equal, because otherwise charge would still be flowing until they were equal. So delta V across the equivalent capacitor is just VL minus VR, or delta V across the battery. Then back to the collection in series, once charge has stopped flowing, we expect this plate to have the same potential as this terminal, and this plate to have the same potential as this terminal. These components in the middle have different potentials, so just for the sake of progress, why don't we give them random names, like maybe we say this isolated component on the left has a potential over the whole conductor of VA. Remember, it's really just a conductor insulated from the other parts of the circuit, so the whole conductor is at the same potential, meaning both plates have a potential of V sub A. And this component on the right has a constant potential of V sub B. Then what happens when we write out the potential differences for each of these capacitors? The potential difference across capacitor 1 with capacitance of C1, that potential difference is V sub L minus V sub A. The potential difference across capacitor 2 is V sub A minus V sub B. And finally, the potential difference across capacitor 3 is V sub B minus V sub R. So what do we do now? We had the potential difference for the equivalent capacitor as V sub L minus V sub R. But here we've introduced a lot of variables, so is there anything we can do to get something that looks like VL minus VR? It turns out if we just add together the potential differences in series, we're going to end up with the potential difference across the battery. Let's give ourselves a bit more room so we can see it better. See, we have a minus VA and a plus VA, which cancel, and a minus VB and a plus VB, which also cancel. And what we're left with is VL minus VR. And VL minus VR is the same as the potential difference across the battery, or just the potential difference across the equivalent capacitor, since that's what we actually care about here. In that case, in electrostatic equilibrium, the sum of the potential differences across all of these capacitors is equal to the potential difference across the equivalent capacitor. So here, with the capacitors in series, we have a sort of inverse situation. Before, the potential differences were all the same, but the charges added up to give you the total charge on the equivalent capacitor. Here, the charges are all the same as the charge on the equivalent capacitor, but the potential differences add up to give you the total potential difference across the equivalent capacitor. So now, what do we do with these equations? We remember that for each individual capacitor, we can say the capacitance is equal to Q over delta V for that capacitor. Before we solved for Q because the Q's were additive, but in this case it actually makes more sense to solve for delta V because the delta V's are adding up. Then it looks like this for each capacitor. Now we can plug this relationship into our equation with the potential differences adding up, and we end up with this equation here. Using our knowledge that the charges are all the same, we can just say the charge on any capacitor is Q, and then write the bottom equation like this. Dividing by this charge Q on both sides gives us our final result that the capacitance of an equivalent capacitor is given by this equation, when the original capacitors 1, 2, and 3 are in series. Once again, very interesting that we went through all those hoops and end up with such a deceptively simple equation. Also keep in mind that this is a solution for the inverse of the equivalent capacitance. If you want the actual capacitance itself, you'll have to evaluate the entire right-hand side, and then take the inverse of that. In the case of n capacitors in series, we just extend this equation out to n capacitors. And again, we haven't proven that extension here, so if you're interested, you should give it a go and try proving it for yourself. So those are our two fundamental ways we can connect two capacitors. If we want to evaluate the capacitance due to a complex system with some in series and some in parallel, we just take it one step at a time, evaluating it piece by piece until we end up with our final result. Let's think about this system right here. So we know how to work with capacitors in series, but do we have any components in series? Here it turns out we actually have none. You might want to say C1 and C2 are in series, but the reason they aren't is because in order for them to be in series, you have to be able to trace your finger along the path that connects them, and you can't have any junctions or points where the wires branch off, like at this point here. This is where we get some wire branching off, so since it's between C1 and C2, they're not in series. By that logic, C2 and C3 are definitely not in series, and neither are C1 and C3, so none of these capacitors are in series with each other. Then our only other option is trying to find two capacitors that are in parallel. Two branches are in parallel if the branches start at the same junction or node and end at the same junction or node. Keep in mind I said branches, not capacitors. We could have a lot of detailed workings inside of the branches that we have to deal with, but in this case, each branch is just a single capacitor. So we see the top branch with capacitor C2 is in parallel with the bottom branch that has capacitor C3. In that case, we should write the equivalent capacitance between 2 and 3 as C2 plus C3. Remember, they just add up if they're in parallel. Now moving on, do we have any branches in parallel here? We don't, because there is no branching off anymore. In that case, do we have any components in series? All we have left are these two components, so if we trace our finger along the path between them, there's no branching off between them, which means these two components here are in series. With series components, we add their inverses and then take the inverse of that, so our final equivalent capacitance is given by this equation. In that case, this last lone capacitor is our equivalent capacitor. We can take this original system of capacitors and completely replace it with this capacitor that has this capacitance, and nobody would be able to tell the difference. One last thing I wanted to make clear, I had these animations showing with charge moving asynchronously from one side to the other, with nothing happening in any of the other components. The reality is what you see here is not how it actually works. Really, as soon as you make the last connection on a circuit, electrons are flowing throughout all of the components at the same time. We'll discuss a much better model for charge flow once we get to the module on current.